An online commenter raised a sharp question. China's used car market has enormous potential, but it will be far more difficult to operate in than the U.S. market. The reason is that the penetration rate of new energy vehicles is too high, dragging down the residual value of the entire market. NEV technology iterates so rapidly that even if a car just sits there undriven, it continuously depreciates simply because new technologies keep emerging, not to mention the fierce price war on new cars. Domestically, although internal combustion engine technology is mature and does not suffer tech iteration depreciation, the constant price cuts on NEVs force fuel vehicles to cut prices as well as new fuel cars become cheaper. They naturally further suppress the residual value of used fuel cars. Doing used car business in China demands extremely high turnover rates. Once a car is acquired and placed on the lot, every extra day it sits there means the asset is shrinking in value. Another commenter observed that in a used car trading market in Fuzhou, a vast sea of zero-kilometer used cars is parked in 5 to 6-story buildings, stretching as far as the eye can see. This leads to a broader judgment. For China's auto industry going global, used car exports may eventually surpass new car exports in the future. The vast developing countries in Asia, Africa, and Latin America will mainly purchase not new Chinese NEVs and fuel vehicles, but Chinese used cars that have only been driven a little over 100,000 kilometers, or even zero-kilometer used cars that are in countries like Belarus. Many families buy used cars that have already been driven over 100,000 kilometers, which then change hands several more times, running up to over 500,000 kilometers, and there are even old, beat-up cars with 800,000 or 1,000,000 kilometers on them still running on the roads. These discussions touch upon a deeper question. When China's ultra-low-priced NEVs disrupt the original price system of European, American, Japanese, and Korean automakers, when you can buy a large SUV that previously cost over 300,000 to 400,000 yuan for just over 100,000. When NEVs phase out fuel car prices are dragged down a level, used car prices follow, and the global used car price benchmark shifts downward overall. What does this mean for the structure of the global auto industry? Furthermore, as the AI technology revolution simultaneously impacts the job market, with deflationary pressure on one side and the infinite possibilities created by new industries on the other, should we ultimately be pessimistic or optimistic? This article attempts to provide a systematic answer based on data and logic that IT is not a simple judgment, but rather breaks the problem down into 6 interrelated dimensions, each supported by concrete numbers and trend. Analysis Point 1. The structural dilemma of China's used car market. The core contradiction facing China's used car market can be summarized as asset deterioration caused by technological iteration. Does this judgment hold up at the data level? The answer is, it basically holds. But it is not evenly distributed across the entire industry. Let's look at the most critical quantitative evidence. The 3-year residual value rate. This is the most intuitive indicator for measuring the asset value of a used car. Data from the China Automobile Dealers Association and Jingzhengu for 2024 to 2025 shows a significant divergence in the residual value rates of NEV companies. Models like BYD Seal and Song Plus have 3-year residual value rates of approximately 55% to 60%. NIO's ES6 and ET5, due to the NT platform generation change penalty, have seen their residual values drop to a low of 42% to 50%. the Xpeng's P7 and G6 because of intelligent driving hardware iteration, which renders old models functionally deficient, have residual values between 45% and 52%. Li Auto is a clear counterexample. Its L-series extended range models have achieved a 3-year residual value rate of 60% to 65%, almost on par with fuel vehicles. For a horizontal comparison, the benchmark for Chinese fuel vehicles, Toyota and Honda, have residual value rates of about 62% to 68% in the U.S. market. The Tesla Model Y's 3-year residual value rate is between 58% and 63%, while GM's Lyriq and Blazer have fallen to 45% to 55% due to software glitches and production halts. Traditional pickup trucks and Toyota are in the 58% to 65% range. This data reveals a key fact. The median residual value rate for Chinese NEVs is about 52%, while for fuel vehicles it is about 65%, creating a gap of as much as 13 percentage points. In the U.S. market, the median residual value for electric vehicles is 55%, and for fuel vehicles about 60%, a gap of only 5 percentage points. This means the Chinese market is far from digesting the risk premium for EV technology depreciation. The capital market is still treating them as inferior financial contracts. Zero-kilometer used cars are another phenomenon worth attention. Data from the China Automobile Dealers Association clearly shows the formation mechanism. OEMs' wholesale volumes based on production capacity planning far exceed terminal retail sales, and the Dealer Inventory Alert Index has been above the 50% boom-bust line for 25 consecutive months, even reaching 63.8% in February 2025. To recoup cash flow, dealers are forced to preemptively register their stockpiled inventory cars, turning them into nominal used cars, and then liquidating them as nearly new vehicles. In the full year of 2024, nearly new cars, defined as less than 1 year old, accounted for 7.2% of used car transactions, equivalent to about 1.41 million vehicles flowing into the used market, with a significant increase in the proportion of zero-kilometer inventory cars. More severely, this proportion was still rising month-on-month in 2025. The proliferation of zero-kilometer used cars has already entered a negative feedback loop that cannibalizes the new car pricing system. New car price cuts make nearly new used cars even cheaper, which in turn makes new cars harder to sell, forcing OEMs to cut prices further. The China Automobile Dealers Association has listed zero-kilometer used cars as a major structural risk for the 2025 market. For used car dealers, this means turnover rate is a matter of life and death. With the Inventory Alert Index persistently above the boom-bust line, average inventory turnover days far exceed normal levels, and every extra day of holding an asset means facing depreciation risk. However, the way out for China's used car market may lie overseas. Used electric vehicles from BYD and SAIC have already been flowing in large numbers to Central Asia, Southeast Asia, and Eastern European markets, with exports exceeding 100,000 units in 2024. In 2025, the average export price of Chinese used cars declined by 6% to 8%, showing a path of low domestic prices, narrowing export premiums, and global price convergence. Developing countries in Asia, Africa, and Latin America are highly price sensitive, and the price advantage of Chinese used cars precisely hits this demand gap. Of course, challenges exist. Local policy restrictions, such as ASEAN's age limits on imported used cars, a lack of after-sales service systems, and insufficient brand recognition. But overall, an arbitrage channel of China clearing inventory and emerging markets absorbing it has already formed. Point 2. The historic shift in global automotive pricing power. If the predicament of China's used car market is a domestic issue, then the restructuring of the global automotive price system is a transfer of pricing power that affects the entire industry. This shift is already clearly reflected in the data. The average export price of China's pure electric vehicles in 2024 was approximately $34,000 per unit, a year-on-year plunge of 12.3%. The average export price of plug-in hybrid vehicles was about $25,000 per unit, a year-on-year drop of 8%. The shockwave of the domestic price war is spreading outward. In the U.S. market, the Manheim Used Vehicle Value Index stood at 205.5 in December 2024, a year-on-year drop of 5.4%, marking 3 consecutive years of decline from its peak of 255 in 2022. Manheim wholesale prices are a 6-month leading indicator for new car retail prices, meaning the decline in wholesale prices signals that the downward shift in retail prices is far from over. Although the Kelley Blue Book average transaction price for new cars in the U.S. remained at $49,740 in December 2024, average incentives per unit have surpassed $3,500, hitting a new high, meaning the effective discount is continuously widening. Multiple authoritative institutions unanimously judge that the era of global automotive pricing deflation has arrived. J.P. Morgan, in its January 2025 Global Auto Outlook, explicitly stated that global automakers' pricing power is at its weakest level in nearly 5 years, predicting a 2% to 3% decline in the average global transaction price in 2025. That a Bloomberg special report directly defined this as the era of global auto pricing deflation, arguing that China's low-cost manufacturing combined with the high interest rate environment has ended the seller's pricing power. Data from LMC Automotive shows that the real transaction price of global light vehicles, adjusted for inflation, has turned negative year-on-year. 2024 was the first full year since 2019 to see a substantial decline in global automotive prices. Tariff barriers, like the EU's tariffs on Chinese EVs and the US's 100% tariffs, will partially impede China's direct exports. But they cannot reverse the overall direction that the global price benchmark is being redefined by China's cost curve. The decline in prices will inevitably stimulate demand growth, especially in price-sensitive emerging markets. Data shows that India's auto sales growth rate is between 6.5% and 7.5%, with a per capita GDP elasticity coefficient of 1.1 to 1.3. This means that every 1% growth in per capita GDP can drive 1.1% to 1.3% growth in auto demand. Southeast Asia's growth rate is between 4.5% and 6%, with an elasticity of 0.7 to 1.0. Brazil in Latin America has a growth rate of about 2.5% and an elasticity of 0.3 to 0.8. If the average unit vehicle price drops by 10%, combined with a demand elasticity of 1.1, India's auto demand could grow by about 11%. The price war is not only a competitive tactic, but also a condition for unlocking incremental demand in emerging markets at the same time. The industry chain is accelerating its relocation to low-cost regions. Chinese automakers are building factories in Thailand and Indonesia, leveraging local labor forces and tariff preferences to radiate into the ASEAN market. BYD's market share in Thailand had surpassed 10% by 2025. India's high tariff barriers are forcing Chinese automakers to seek joint venture or technology licensing pathways. The localized production of Chinese brands in Brazil and Mexico is also accelerating in the short term. New production capacity adds to the pressure of oversupply, further depressing prices in the long term. Localization reduces costs and improves accessibility, activating demand that was previously suppressed by high prices. Point 3. How big is the real impact of AI on employment? The discussion surrounding AI replacing jobs is filled with conceptual confusion. This is the biggest statistical trap in all current AI employment discussions. Let's look at the core data from various authoritative institutions. In its classic 2023 report, Goldman Sachs pointed out that roughly 300 million full-time equivalent jobs globally are exposed to the technical influence of generative AI. This figure is often misread and cited as AI will wipe out 300 million jobs. But in reality, this is an exposure rate to tasks, representing the technically automatable upper limit, not an actual unemployment forecast. In its updated reports from 2024 to 2025, Goldman Sachs made its position clear. AI will not cause a spike in unemployment, but will instead boost overall labor demand. Latest report in February 2025 even warned that too much is being invested in generative AI for too little gain, emphasizing that the productivity payoff is slower than expected, making a wave of layoffs even less likely. An IMF working paper from 2024 shows that about 60% of employment in advanced economies is exposed to AI, and about 40% globally. But the IMF explicitly wrote a correction in the very same report. Only about half of these exposed jobs face substitution risk, while the other half may benefit from AI augmentation. The most commonly misread clause from the IMF happens to provide official testimony to the confusion between exposure rates and unemployment rates. Data from the McKinsey Global Institute shows that 60% to 70% of employee working hours will be touched by generative AI, but the net unemployment prediction for 2030 is approximately zero under its baseline scenario, because the 15% to 30% of working hours automated will be offset by newly created work. McKinsey's core metric is not a job loss figure, but the estimate that the U.S. will need roughly 12 million occupational transitions. This is a transformation, not unemployment. In their 2024 to 2025 updates, none of these three institutions provided a single net job loss number for the claim that AI will eliminate X million jobs globally. They have all shifted to scenario analysis. And under their baseline scenarios, they all lean towards an AI augmentation-dominated outcome, where the macro-level net unemployment is near zero. But does this mean AI has no substantial impact on employment? The answer is no. The proportion of jobs exposed to generative AI is as high as 15% to 20%. Far exceeding the 5% to 8% substitution rate during the IT revolution from 1990 to 2000. This means the magnitude of the shock is larger. Moreover, the nature of AI's impact on Employment is changing. In a 2025 NBR working paper, MIT Starin Asimoglu proposed a key argument. Current AI systems are excessively biased towards substitution and lack the capacity to create new tasks. This is the wrong type of AI, and the path direction determines the net effect. His model estimates that, along the current technological trajectory, the net impact of AI on labor demand is zero or slightly negative, with a 10-year total factor productivity gain of only 0.53% to 0.6%, far below what optimists predict. Meanwhile, in multiple 2025 papers, economist David Autor pointed out that the biggest difference between generative AI and the Internet era lies in the scope of the shock. In the past, the IT revolution substituted routine tasks, complementing high skills and substituting low skills. Now, generative AI has for the first time swept cognitive judgment tasks like programming, writing, translation, and legal analysis into large-scale substitution risked. High-skill knowledge jobs are no longer an immunity zone. The historical experience of the Internet era provides an important frame of reference. Between 1947 and 1987, the annual substitution rate was about 1.5%, but the annual emergence rate of new tasks was about 2%, leading to a 0.5% annual net increase. In labor demand, the annual job creation rate was about 1%, far lower than the gross substitution rate of 6% to 8%, but net absorption was achieved because of its long duration. For every old job destroyed, about 2.4 to 2.6 new jobs were created. However, Asimoglu emphasizes that the current AI systems lack task creation capability, meaning AI excels at substituting but not at generating new types of tasks. This constitutes an essential difference from the Industrial Revolution and the IT Revolution. Point 4. The tension between short-term deflation and long-term prosperity. The shock of AI on the economy is first manifested on the deflationary side. China's core CPI has been operating at a low level for a long time, with a year-on-year increase of roughly between 0% and 0.6% from June 2025 to June 2026, while the PPI has been in persistent deflation, with a year-on-year negative growth of between 1.4% and 4.5%. The squeeze on wage income from AI substitution is intensifying demand-side deflation. The IMF predicts that the global labor income share will drop from 53.4% in 2023 to between 51.8% and 52.3% in 2029. This means labor's share of GDP is continuously declining, suppressing consumption capacity. AI substitution acceleration is listed as the primary structural factor depressing the labor income share over the next decade. The Chinese Consumer Confidence Index was in a low range in June 2026, reflecting employment uncertainty and weak income expectations. But this does not mean there is no hope in the long run. Looking at historical patterns, every technological revolution has undergone a similar process. The agricultural revolution increased the land carrying capacity from 0.01 people per hectare to 0.1 to 1. The Industrial Revolution boosted per capita output by 10 to 100 times. The Information Revolution enabled global knowledge sharing and made services tradable. In the early stages of each transformation, structural unemployment and rising income inequality occurred, and machine-smashing movements even happened during the Industrial Revolution. But each transformation ultimately created more and more productive Employment. The structural transformation of employment from agriculture to industry took about 200 years in the UK, with agriculture's share of employment dropping from 80% to 10%. The shift from industry to information services took about 80 years in the US, with manufacturing's share dropping from 35% to 8%. If we follow the law of historical acceleration, where each transformation cycle is halved in time, the transition from the information age to the AI age could be completed within 30 to 50 years. But the growing pains of this transition, particularly the fact that job substitution is faster than job creation, may be concentrated in the first decade, 2025 to 2035. The transition from short-term deflation to long-term prosperity requires three preconditions. First, future AI systems must evolve from a substitution type to a new task-generating type that spawns novel human occupations. There is currently no clear evidence of such a leap. Second, the speed of reskilling and retraining systems must match the pace of the transformation. The transition window in the Internet era was 3 to 5 years. In the AI era, the window may only be 1 to 2 business cycles, demanding a 5 to 10-fold increase in retraining system efficiency. Third, if AI gains are concentrated in the hands of capital and technology owners while the labor income share continues to fall, a paradox of production boom and consumption deflation will emerge. Universal basic income and an AI taxation regime may become necessary options. Point 5. The employment capacity of future emerging industries. Pessimists worry that AI is destroying jobs. But from another perspective, industries that do not exist today may create employment several times over what is being substituted today. The robotics industry is the most definitive source of increment. Data from the International Federation of Robotics for 2025 shows that global industrial robot installations reached 541,000 units in 2024, an 11% year-on-year increase. Global revenue for service robots was $29.1 billion, a 5% year-on-year increase. Humanoid robot installations are expected to reach about 200,000 units per year by 2030. More crucial is the employment effect. In the service robot sector, between 2025 and 2026, about 8.2 million jobs will be substituted, while about 9.7 million jobs will be created, resulting in a net creation of approximately 1.5 million jobs. The VR and AR industries are moving from concept to reality. IDC's tracking report from the first quarter of 2026 shows that total AR and VR headset shipments reached 8.6 million units in 2025, a year-on-year growth of 34.5%, with market revenue of $9.20 billion. Content development jobs numbered around 650,000 in 2025 and are projected to grow to 2.4 million by 2030. Remote operation jobs will soar from 500,000 in 2025 to 3 million in 2030. 3D content creation and modeling jobs will increase from 250,000 to 300,000 to 1. 000 000-1 200 000. Interaction designers will grow from 100,000 to 150,000 to 400 000-500 000. Hardware engineers will grow from 150,000 to 200,000 to 500 000-600 000. The overall employment capacity of the VR and AR industry chain will grow from 1.05 to 1.25 million in 2025 to 5.4 to 6.1 million in 2030, a staggering compound growth rate. The penetration of digital twin technology is accelerating. The market size was approximately $10 to $15 billion in 2023, with a compound annual growth rate of over 30%. Manufacturing and smart city sectors have already achieved a 20% to 30% primary penetration, including applications like digital mapping, simulation, and predictive maintenance. BMW's iFactory and Siemens digital factories are mature case studies. Xiong'an New Area and Singapore's Virtual Singapore represent explorations at the city-level digital twin scale. Although deep penetration for full life-cycle closed-loop management is still in its early stages, digital twins are becoming an infrastructure of the real economy. Gene editing and synthetic biology represent another underestimated track. The global synthetic biology market was around $20 to $30 billion in 2025 and is expected to reach $50 to $80 billion by 2030, with a CAGR of 20% to 30%. 2 to 3 CRISPR gene editing therapies have been approved, such as Casgevy for sickle cell disease, with over 50 pipelines under research covering genetic diseases, cancer, and cardiovascular disease. The industrial bottlenecks are delivery technologies, off-target effects, and high treatment costs. Casgevy is priced at about $2 million per course of treatment, limiting mass adoption. But the technological path is clear. The space economy is also moving from research to industry. Total global space economy revenue grew from $630 billion in 2024 to $780 billion in 2025. That direct global employment is roughly 500,000 to 600,000. The first crewed lunar flyby missions and commercial space station operations between 2026 and 2028 could push employment to 700,000, 800,000, asteroid mining trial extraction and permanent lunar bases between 2030 and 2035 could bring employment to 1 to 1.5 million. Crewed Mars exploration and the early formation of a solar system economic zone between 2040 and 2050 could see space employment reach 3 to 10 million. In more terrestrial domains, there is also quantifiable progress in desert transformation and extreme environment development. The cumulative managed area of the Kabuki Desert in China exceeds 6,000 square kilometers, with a unit management cost of about $3,000 to $5,000 per hectare. The technical model, combining photovoltaics, sand control, and planting, has already achieved commercial viability. Saudi Arabia's NEOM, with a planned area of 26,500 square kilometers and an investment exceeding $500 billion, involves vertical desert farming and solar-powered desalination. But the unit development cost of $100,000 to $500,000 per hectare makes its replicability questionable. The Qinghai-Tibet Railway extension and the commercialization of the Arctic shipping route are advancing, but large-scale human habitation still requires breakthroughs in low oxygen and extreme cold technologies. 6. The integration of the virtual and physical worlds, the metaverse, and digital twins are not just concepts for entertainment. They are changing the way humans interact with the physical world and creating an entirely new economic space. From a technological maturity perspective, progress varies greatly across different fields. Industrial digital twins have achieved scaled deployment, with a maturity score of about 8 out of 10. BMW's iFactory and Siemens digital factories Our benchmark cases, city-level digital twins, are in the pilot stage. With a maturity score of about 5 to 6, the human body digital twins are in the research stage. With a score of 3 to 4, remote surgery has seen over 100 successful 5G cases in China. But its maturity is only 4 to 5. Remote operation of heavy machinery is quite mature in mining and ports, with a score of 6 to 7, as exemplified by Rio Tinto's remote mining and Shanghai's automated Yangshan port. What is the economic scale of the metaverse? Predictions from different institutions vary wildly, which in itself is a classic sign of a forecasting bubble. PwC's estimate is roughly $320 billion for 2025, including indirect pull. The OECD's estimate is roughly $200 billion, including only direct spending. Independent third-party comprehensive estimates fall between $100 billion and $350 billion. Extreme bull case scenarios from investment banks, such as Morgan Stanley, have given an $8 trillion total addressable market ceiling. But this figure includes all digital economic activities and is not a direct consumption metric. The gap between investment bank forecasts and actual third-party data is fundamentally a clash between top-down emotional narratives and bottom-up factual tracking. Brokerages assume all digital activity morphs into the metaverse, effectively stuffing all global e-commerce, advertising, gaming, and social media into the metric. This is the maximum imaginable space. Third-party agencies only count invoiced spending like headset shipments, enterprise AR software, and real-time engine subscriptions. Both are correct, but they answer different questions. Mistaking a brokerage forecast for a baseline turns a bubble into a floor. The metaverse GDP in 2025 is still in an early startup stage, accounting for about 0.2% to 0.5% of global GDP. By 2030, it could reach 60 cents to $1.20 trillion, or 0.5% to 1% of global GDP. It does not yet have the scale to substitute the real economy. However, its compound growth rate is between 30% and 50%, far higher than traditional industries, and its long-term potential cannot be ignored. The most important significance of the virtual world may not lie in entertainment, but in its ability to extend human operational capability to places physically inaccessible. Through VR glasses, AR glasses, haptic feedback, force feedback, and temperature and smell sensors, a person can perceive and manipulate real equipment thousands of miles away from here and now. Remotely controlling a plant factory and solar power plant in Earth's orbit from the ground, or maneuvering a surgical robot in an operating room hundreds of kilometers away from an office to operate on a patient in a remote area. These scenarios have moved from science fiction to engineering verification. Point 7. Does optimism in the AI era hold water? The final dimension of the discussion, and the most fundamental debate. Will AI ultimately make humanity better or worse off? The pessimist concerns are reasonable. The speed of AI substitution may outpace the speed of creation. The labor share of income will continue to decline, global consumption capacity will shrink, and the deflationary spiral will reinforce itself. The automotive price war and factory layoffs are just the tip of the iceberg, and the collapse of more traditional industries may be on the way. But the optimist's argument also has its logical basis and historical support. Every technological revolution has sparked similar fears, and every time, humanity has found a new path to growth. The key lies in understanding the expansion pattern of the boundaries of human activity. The agricultural revolution domesticated plants and animals, increasing the land's carrying capacity by 10 to 100 times. The Industrial Revolution harnessed fossil fuels and mechanization, boosting per capita output by 10 to 100 times. The Information Revolution achieved global knowledge sharing through the Internet and automation. The AI revolution is expanding cognitive bandwidth and decision-making quality. This is an upgrade to human capital itself, not a simple substitution to the macro level. The resources that humanity has not yet developed or utilized are immensely vast. High-altitude, uninhabited zones, extreme cold regions, the deep sea, deserts, and space. These areas contribute almost no GDP today. With the assistance of AI, humanity has the potential to develop and utilize these resources 100-fold or 1,000-fold. That semi-underground cities could enable human settlement on plateaus and in polar regions. Closed-loop ecosystems could establish agriculture and industry in deserts. Space-based solar power stations could provide the Earth with a near-infinite supply of clean energy. Every single direction requires tens of millions, even hundreds of millions, of laborers to design, build, and operate at the micro level. Gene editing and molecular design are opening up an entirely new dimension of resources. When humanity, assisted by AI, can design new species and new materials, manufacturing costs will decline exponentially, while function and performance will increase exponentially. The labor scale required by new industries, such as synthetic biology, cellular agriculture, and biomanufacturing, is unimaginable from the perspective of today's manufacturing sector. There is another dimension that is generally underestimated. The virtual world itself is an economic resource created out of thin air. Building digital twin cities, metaverse spaces, and virtual worlds requires massive amounts of content creation, interaction design, and system operation and maintenance. These job positions do not exist today, but they may become one of the most dominant forms of employment in the future. Regarding the scientific basis for solar system development and population carrying capacity, based on O'Neill's cylinder designs and the massive material resources in the orbits of Jupiter and Saturn, the solar system could theoretically support trillions of people. But this scale would take 200 to 500 years to achieve, and the required energy, materials, and life support technologies have yet to break through. What is more feasible in the near term is lunar water ice mining to provide fuel and life support water sources. Mars settlement could be realized between 2040 and 2060, a judgment supported by SpaceX's timeline. The economics of asteroid mining are still being validated. The break-even point for recovering platinum group metals from near-Earth asteroids is about $5,000 to $10,000 per kilogram, whereas the current terrestrial mining cost is about $2,000 to $5,000 per kilogram. So space mining is not yet cost competitive. However, water ice mining in cislunar orbit is already economically feasible, with breakthroughs expected between 2028 and 2032. Progress in artificial womb technology also offers new possibilities for long-term population development. That at least 6 teams globally are researching full artificial wombs, having already achieved midterm survival in lambs, pigs, and mice to AS of 2026. No human clinical trials have been approved. Ethical hurdles include the legal status of the fetus, the risk of interrupting the maternal-fetal connection, and unknown long-term developmental effects. Human clinical trials could potentially start between 2028 and 2032, with the earliest commercial application between 2035 and 2040. The estimated timeframe for completely replacing natural gestation is after 2050.8. Where do the core uncertainties lie? Between optimism and pessimism. Four core uncertainties will determine the direction of the next 30 years. The first uncertainty is whether AI's task creation capability will emerge within the next decade. This is the most critical variable determining the employment trajectory from 2030 to 2040, the optimistic camp at McKinsey believes. AI will create a large number of new jobs through augmentation, leading to net positive employment. The empirical camp, represented by Acemoglu, believes that current AI is a substitution tool that lacks the ability to create new tasks, leading to net employment that is zero or slightly negative. These two views are difficult to reconcile, reflecting a fundamental divide in academia over the nature of AI. If AI remains positioned purely as a substitution tool, then short-term deflation could evolve into long-term stagnation. If AI evolves the capacity for task creation, then the explosion of new industries after 2030 will far exceed what we can imagine today. The second uncertainty is the timeline for the commercialization of nuclear fusion. This determines the limits of energy costs and economic growth. Cheap energy is a prerequisite for all industrial expansion. Desert transformation requires enormous energy for desalination and environmental control. Space development needs low-cost propellant. The real-time computation of digital twins demands massive electricity supplied, and if nuclear fusion is commercialized before 2040, the resource constraints facing humanity will be greatly relaxed, making the optimist's vision much easier to realize. The third uncertainty is whether the global governance system can cope with technological unemployment and wealth polarization. Even if AI ultimately creates more jobs, the structural unemployment and income inequality during the transition period will create immense social pressure. Historical experience shows that institutional innovation, education system reform, social safety nets, retraining infrastructure, is a necessary condition for the smooth landing of a technological revolution. Universal basic income and an AI taxation regime may move from academic discussion into policy practice. The fourth uncertainty is whether geopolitical conflicts will interrupt the restructuring of industrial chains and the development of emerging industries. The U.S.-China tech decoupling, regional trade barriers, and the fragmentation of technical standards could all slow down the restructuring of the global automotive pricing system and the development of new industries. Tariff barriers can delay but not reverse the trend, but sudden geopolitical changes could alter the development path. Taken together, a three-phase judgment framework might be the most explanatory. Short-term deflation, 2026 to 2030. AI substitution pressure intensifies. Consumer deflation persists. The labor income share falls. The price war on used and new cars hurts asset prices, and emerging industries are still in their early stages and insufficient to absorb the unemployed midterm growing pains. 2030 to 2045. If AI's task creation capability starts, new industries will rise. Jobs like remote operations, digital twin operation and maintenance, and AI trainers will become new employment growth points. Synthetic biology and gene editing will enter a mature phase. But structural unemployment and wealth inequality may peak. Long-term optimism, 2045 to 2100. The space economy shifts from research to industry. The metaverse and digital twins become important components of GDP. The potential infinitude of energy may greatly relax resource constraints. The boundary of human activity expands to the scale of the solar system. Ultimately, on the question of the AI age's future, the most persuasive argument may be the lesson offered by history. Before the Industrial Revolution, agriculture was virtually the only major human industry, and most GDP was concentrated there. From today's perspective, the total economic output of non-agricultural industries is many multiples of that of agriculture. Standing 50 years in the future and looking back at today, the total share of all of our current industries combined might only be equivalent to the share that agriculture holds in the economy today. Various new industries that do not exist today will, 50 years from now, generate a GDP that is hundreds or thousands of times greater than that of all of today's industries. But this does not mean we can just lie back and wait for the future to arrive automatically. Point 3 conditions must be met. Simultaneously, the evolution from substitution-type AI to AI that can create new tasks, a tenfold increase in the efficiency of retraining systems, and an institutional and distribution mechanism that ensures the dividends of technological progress are not monopolized by a select few. The absence of any one of these conditions could lead from deflation to long-term stagnation rather than long-term prosperity. The automotive industry has already sent a signal in advance. The technological iteration of new energy vehicles is redefining what a valuable asset is. The global pricing system is being restructured by China's cost curve, and the used car market is undergoing a transformation from local transactions to global circulation. These changes are both a microcosm of the economic transformation in the AI era and a lens through which to understand the future.